Hey, this is Duff. Welcome back to my channel. And yep, we're taking another trip back to the surface of Mars. We're going to look at some ancient Mars landscapes, and we want to ask the question, how long have these rocks been exposed at the surface? Like these rocks you see right here in the scene in front of you, how long have these rocks been sitting there? Like, how would we be able to tell that? Well, we've got this Curiosity rover that's in this massive crater, the Gale Crater, that has been collecting data. And one form of data it has collected has allowed us to estimate the amount of time that these rocks have been exposed at the surface. And that's going to give us a little hint about how old the surface of Mars is, or really what the rate of change is in terms of the surface topology of Mars. So we've got ancient Mars landscapes. We're going to look at cosmogenic dating, which helps us reveal that ancient surface. So NASA has this rover about the size of a VW Beetle right here. This is actually a self-portrait it took on the surface of Mars, right? This isn't AI. This is a real picture from the surface of Mars. And that rover has been making its way across the floor of a massive crater on Mars called the Gale Crater. And it's been doing that since 2012. So for 13 years, it's been traversing the inside of this crater. It's now climbing up a mountain that's in the center of that particular crater. And it's closely examined a wide range of different rock types. I mean, that's one of the reasons it's there, is to look at the different rock formations and infer the history of Mars by looking at those rocks. And it's also collected a wide variety of different kinds of data from those rocks because it's been able to drill into them. In fact, if you look carefully, you can see right here on this rock, there's a little hole that looks kind of unnatural once you notice it. That's actually a drill hole. And it's drilled down, brought up material from inside that rock, and then it's storing it away inside. Well, actually, you can put it in some analysis tubes and actually look at the chemistry inside that rock. What has Curiosity discovered? All right, from water-infused bedrock, water deposit conglomerates, wind-formed dunes to some active dunes that are there, Mars has shown to have a very dynamic past. There's large valleys, there's cliffs in Gale Crater. They reveal extensive erosion, mostly by wind, we would think. In fact, the extent of observed erosion is so great that NASA scientists believe that it's taken at least several hundred million years to erode and expose the current rock surface you're looking at right now in this particular crater. Now, before I continue, just let me show you a couple other things about like the location we are on Mars. So this is Gale Crater, a 165-mile diameter meteor impact crater, which is highly eroded. Estimates are that this original crater or the original impact would have happened several billion years ago. So this is a very, very old crater. And that little circle there, that little blue circle you see, and the green dot, the blue circle was the target zone, all right, in terms of like bringing the satellite, dropping off this particular rover onto the surface. And the green dot is actually the point that they hit. And since then, it's been working its way across the bottom of the crater, and then it's climbed up gradually into this particular mountain in the middle here. Now you're actually on the surface, and this is an image taken by Curiosity rover not very long after it landed, looking into the hills of the mountains that are in the center of the crater. And you don't have to be a geologist to recognize that there's some different kinds of rocks here, right? There's different colors, probably represent different chemistries of the rocks. And it's pretty obvious that there's some layers in here too, right? You see some horizontal lines. So the erosion, it doesn't all erode equally, which suggests, again, different compositions of the rocks in horizontal layers. That's like some kind of sedimentary rock. So really, and this is really a very impressive bit of topology, in the center of this particular crater. So you might wonder, how can scientists sitting on Earth look at these rocks and have any idea like how old they are? Sure, there's the appearance of a lot of erosion. So you're like, yeah, that looks like it could have taken a long time, especially since this is wind that has probably eroded. Everything you're seeing in this image is the product of wind erosion, along with some thermal cracking of minerals and so forth. I mean, there's some other factors, cosmic rays, that can erode material, but this is primarily a wind-driven process. And so you might wonder, like, how long does it take to erode a rock on other planets. Now, a few years ago, I wrote a blog post. And in that blog post, I interviewed a Martian rock, a rock that was just laying on the surface. And I had a conversation with it about, like, how did you get here? Like, where did you come from? And more importantly, like, how long have you been sitting there? And have you always looked the way you have looked? It was really a fundamental question about erosion and about origins, right? The origins of, like, we could ask that question about this picture. What are the origins of these different layers? And at that time, that rock didn't give me a very precise answer, because of course I didn't know what the answer was, since there hadn't been any research on those rocks and the erosion rates hadn't been estimated. But we have done some estimates now today with some very clever ways to determine roughly what the erosion rate is on the surface of Mars now. Right? The Curiosity rover that we sent to Mars has some really sophisticated analytical instruments on board, which have allowed us to answer some of our questions. One of them can take drilled rock dust. It can heat it up until it melts. And then what does it do? It actually smells the molecules that emanate from the melting crystals. Right? And from that, right, it can measure very precisely the ratio of isotopes of different forms, which are different forms of an atom. And that allows it to calculate radiometric ages of some of these rocks. The precision of this instrument isn't, not nearly as good as we have here on Earth, but nonetheless, it's a pretty impressive achievement that just a small car-sized robot on the surface of Mars can collect samples and do this type of analysis. And it gives us our first, direct test of the age of Martian rocks, and even allows us to infer potentially rates of erosion of these rocks. These first radiometric dates are reported in a paper titled In Situ Radiometric and Exposure Age Dating on the Martian Surface, published in the journal Science. And it provided potassium-argon radiometric ages for the rocks that make up the original basement rocks of the Gale Crater, because they're right down there at the bottom of the crater at this point, in the deepest layers of rock that are exposed. And then they also provided an estimate of erosion. So what was that date that they got for the age of the rocks? Now, they estimated somewhere just over 4 billion years old, right? On order of the oldest rocks that are found on Earth. So that really ancient date wasn't all that surprising. It was kind of what was predicted to be found. But what I think was really interesting is that the form of dating that they used also allowed the scientists to estimate how long it's been since a particular set of rocks have become exposed to the surface. That's a different question. The question of how long has this rock, right, especially we focus on this big rock over here, right? And you were to ask, how long has that rock been at the surface? Everything you see in this picture, this lower part of the picture, has clearly been covered up by higher layers of rock at one point. In other words, there's a point right behind this picture where there's a little bit of a hill that has layered rocks in it. And so this whole area has been exhumed, right? This whole area has had erosion happened. Then that erosion exposes these rocks. And so the question that I'm asking here is, how long have they been exposed? In other words, how far back would you have to go in time to find that there was another layer of rock on top of this rock that is now eroded, exposing this particular rock? How far back would you have to go? So there's an astronomy, I'll say, reporter, Emily Lakdawala. And she has written a number of articles about these, the scientific reports that come out of these different places. And so I'll use her summary of what she found about the significance of these dates. So she had a blog post entitled Curiosity Results at AGU, which is a conference. Gale Crater rocks are old, but they've only been exposed recently. Right? So the rocks themselves are very, very old. These rocks were put into place a long time ago, but they've only been exposed fairly recently. Erosion has only reached down to this point sometime more recently than the actual age of the rocks. All right, so how do we address that question of how to test how long a rock has been exposed? Which again is the question of, when did it appear? When did it appear on the surface? And I'm going to allow her to explain that to you, because she's going to explain cosmogenic dating. Mars lacks a significant magnetic field, so anything on its surface is exposed to bombardment by galactic cosmic rays, right? Much more so than you and I are exposed to here on Earth. Galactic cosmic rays can produce significant isotopes of noble gases, argon-36, neon-21, and helium-3. You see, their cosmic rays are high energy particles that come down and they strike the surface of Mars, or the first thing it reaches that is more dense, right, than the atmosphere. I mean, they are striking the atmosphere as well, but a lot of the cosmic rays reach the surface. Once they reach the surface and they hit those rocks that are more dense, they come into contact or interact with molecules in the rocks, well, the rock surfaces, that's what's important here. And in doing so, they produce a bunch of gases, argon-36, neon-21, and helium-3. These gases would not have been present in the rocks when they first formed. Okay, so when the rocks were laid down, like as sediments at the bottom of a lake, these gaseous atoms wouldn't have been present there. And so if you know the rate at which isotopes are produced on Mars, and if you measure their abundance in the current rocks, you can estimate how long the rock has been exposed at or near the surface, right? If you have an estimate of how many of those new atoms are being formed, and that just requires a general estimate of the number of cosmic rays that would be striking the surface, all right? And that's something that you can gather some data in order to get a reasonable estimate of that. And then you measure the abundance in the rock itself of neon and helium and argon that is now inside the rocks itself. It's like encapsulated in the rock. So you've drilled into the rock, you pulled out the crystals from the rock, and now you're going to melt that rock. And that's the deal. Melting the rock releases the gases. The instrument smells the gases and can add up the total amount of material in that particular rock. And from that, you then know how long that rock has been at the surface. Because the rock is, a foot below, it's not getting the cosmic rays and it's not building up those gases inside the rock. So the more gas, right, the more of these elements that are in the rock, the longer that rock had been sitting there exposed to cosmic rays. And this is called cosmogenic dating, right? Cosmogenic dating. So this little simple illustration shows how it's used on Earth in order to look at different rocks that are at the surface. And not all rocks have been at the surface for the same amount of time for the very reason that's shown in this particular figure. You have you've got some kind of substrate, like let's just say it's sand, and you have some stones in that sand. If there's a stone on the surface, it's receiving cosmic rays, and so it's building up different gases, right? Isotopes in them. And then over time, what happens is you have erosion of the sand, but the stone is much harder, so it remains on the surface. But eventually these other stones are rising up. They're not actually rising. The sand is being moved away, right? Is being eroded away. And eventually these other rocks come to the surface. And if you date each one of these rocks using cosmogenic dating, you can actually tell what order they used to be in terms of in the column, in the sedimentary column. So what did she conclude? So continuing on with what Emily has to say about this in describing this research. You can imagine how relatively weak mudstones of the sheepbed unit are getting sandblasted away by wind scouring. And that's undercutting the more resistant layers like Gillespie Lake. All right, she's talking about actually the layer of sediment that's underneath that. Let me go back and show you that. I don't know how easy it'll be to see here, but this harder layer, the Gillespie Lake sandstone right here, and then there's this layer of mudstone, it's called. So it has a different texture, is a different composition, right? And it seems to be not as consolidated, not as lithified, and as a result, more easily eroded by the wind. And that's why you get these chunks of rock that are breaking off, because the Gillespie Lake sandstone is a little bit harder. So she's saying, like, you can see how the sheepbed rocks are being exposed by a process of scarp retreat, right? As the stuff underneath wears out or it gets eroded out, then eventually the top layer is the rocks on top are heavy and eventually break off. As they break off, they're going to expose the new rocks, right? New rocks to the surface, allowing the clock to begin again. If you follow the direction of the wind, then until you get to the scarp, that'll take you to the sheepbed rocks that should be freshly exposed. You can estimate the rate of scarp retreat, and that's about 1 meter per million years. So they're measuring the amount of when the sheepbed unit the Gillespie sandstone above breaks off, and then that's going to expose the rock below to cosmogenic rays for the first time because they were shielded. And so if you go out a little ways where it already is exposed completely, and you ask the question, how long? So you drill several different places. And you know that the wind direction is, you can kind of see just from looking at the way the rocks are being eroded, the wind must be one direction most of the time. And so you can look, you can see like, okay, these rocks are eroding back, from this lower elevation to this upper elevation, they're eroding back. And if I measure different locations and I get the ages of exposure, well, this was exposed at this amount of time. And then I get closer to the cliff, that overhanging rock, that's been exposed for less time. And then right where it's overhanging, it's been exposed for the least amount of time. And so I'm drawing out how it's eroding back. And as it does so, the farther you're away from that particular edge, the older that rock should be, or the longer it should have been exposed at the surface. Okay, now you do all that, you get your dates, right? You take your measurements, you drill a bunch of holes, you collect your rock, and you melt it, you expose, you measure the gases, and sure enough, the rocks that are farther away, right, that have been exposed longer to the cosmogenic rays, the more radioactive, the more isotopes there are. And then as you get closer to the area where it's not, you don't have exposure to cosmogenic rays, sorry, I'm having trouble with my words today, there's much less of those noble gases. All right, what's the takeaway of all that? You can estimate the rate of scarp retreat, right? The amount of distance divided by the amount of time, right? From one point to another. And what you get is, you get an estimate of about 1 meter of rock is being eroded back, right? These little shelves of rock are being eroded back at 1 meter per million years. 1 meter per million years. It's like, I feel like I got to say it a couple times. 1 meter per million years. This type of analysis is done for rocks on all over the Earth. And like I said before, it's called cosmogenic nuclide dating. And it does allow for these very rough estimates of the rates of erosion or exposure times at different locations. The question is, how fast are rocks eroding, like in a place like Utah or other deserts in the world? Like, how long has desert pavement existed in the Sudan Peninsula? I think the operators of the Curiosity rover have come up with, a really nifty way to estimate erosion on the surface of Mars. That 1 meter per million years, it's a pretty rough estimate because the precision of the instruments that are there on Mars aren't nearly as precise as our instruments here on Earth. Regardless, this data reveals that erosion really is happening on Mars, but you might think that 1 meter per million years is a really slow place. But remember, the atmosphere is really thin on Mars, and there's only wind and freeze-thaw cycles and that, cosmic rays. Those are the primary forces that are available to change the surface of Mars. They're not very powerful forces. They're going to work very slowly over time. So now, if I go back to my Martian friend, who I'm probably going to talk to in another video, right? We're going to have a long conversation with this rock here and discuss how it came to be. It's an interesting rock because I don't know if you see that here. If you know anything geology, you look at this rock, you immediately go wonder, that looks like a conglomerate. A conglomerate is a conglomeration of multiple pebbles, all right, with maybe some media in between, like some sand, and then that all became hardened together. And so it suggests the formation of rocks that eroded, turned into pebbles, and then those pebbles got deposited somewhere else, and then that all got consolidated or got lithified into a rock itself. And now that rock is eroding. And you can kind of see, it's eroding. That conglomerate is sort of falling apart over time because there's some little pebbles around it that probably were part of that rock. And so the question you could ask is like, well, how long is that Is that thing going to continue to be there? So one of the questions I asked this rock was, I thought, what's going to happen to you in the future? Like, what is your future? And here's how it responded. Well, assuming you don't poke me or shoot me with your little laser toy on your way by, of course referring to the Curiosity rover, which took a picture of it, I might expect to hang on for another 10,000 years, maybe several 100,000 years, referring just to this rock here. After which, I'll probably have completely fallen apart into all those little stones that I was originally made of. Now, those little stones, they're just a whole lot tougher than I am. And so the wind and thermal tension probably isn't going to be able to tear them down so quickly. So someday you're probably just going to find a little pile of stones here, maybe spread out a little bit as they're pushed around by the wind, or maybe sand might cover them up over time and then might uncover them later in time. On the other hand, it's possible that, another possibility is another meteorite could hit right near this rock or hit right on top of this rock and then cover it with a blanket of new rocks. In that case, this rock would have some new friends, right? That would shield him from erosion, and maybe it would last longer as a result. Now, this rock is also building up cosmogenic nuclides, right? Through those cosmic rays hitting it. So if it gets covered again, then the timing will stop, right? Because it won't be receiving more of those, it won't be making more of those isotopes. And then when it gets uncovered again, the clock will start again. And that's why the clock isn't, perfect, because all it tells us is how long it's been totally exposed at the surface. So if you estimate that a rock formation has been exposed for 2 million years at the surface, it could have been 1 million years exposed at the surface. Then it could have gotten covered for 1 million years. And then it could have gotten uncovered and been around for another 1 million years. So that's actually 3 million years that rock was there since it was first exposed. So it's complex. You can't know the exact history. What you do know is generally like how long it has been exposed, whether it's been exposed for one continuous amount of time or whether separate amounts of time or separate time intervals. So I think that this prediction of like 10,000 years or a bit longer, that seems kind of about right based on this estimate of the rate of erosion of a meter over 1 million years. This is actually a fairly small rock. It's only like 6 inches in size. And it's also sitting up on top of the surface, and it's made up of, the sand holding it together. Like I said, the pebbles themselves probably are going to be around for millions of years. Still, this little rock is just but a small little piece of the geological terrain in an area that includes many small meteorite craters and many hundreds of meters of rock that have been eroded in the area before our little friend even came to find itself at this particular position. Right? This rock sits on many, many, many feet of sedimentary rock. But as you look around, there's hills around where this rock sits that are hundreds of feet high, made up of sedimentary layers that surely were covering this spot where this rock sits right now. So the Curiosity team has now collected enough evidence to convince them that the rover is now driving around on rock that was deposited originally as sediments in a large lake. But that large lake has been dry for hundreds of millions, if not potentially more than 1 billion years. Since there's a massive amount of rock that is eroded and new small craters have been created inside of the crater, and then they've been covered up with even more debris, and then there's been other cratering events. All this while wind has slowly been eating away at the rock surfaces, moving material around from one place to another. So if we looked at a snapshot today and came back 1 million years from now, I think it would look, the scene you're looking at right now would probably be very, very similar. I mean, if they're right, 1 meter over 1 million years, there'd be about 1 meter of rock difference in some of these locations. A little bit more in some places, a little less in other places. But standing back and looking at the big picture like you are here, you probably wouldn't see many differences 1 million years from now. So yeah, Mars, I think you can say that it's a dynamic planet. You can see valleys. You can see that there's volcanoes. You can see that there's highly eroded craters. There's other craters that are brand new. There's craters that we know have come into existence within the last year because we've taken satellite images of the surface of Mars, taken another satellite image a year later, and seen new spots that's been struck by objects. So it's dynamic in the sense that much change has happened to Mars. But that dynamism is expressed over millions, hundreds of thousands, millions, and even billions of years. And look at this scene before us here, right? The idea that all this rock, probably this whole thing you're looking at, where you're standing here, where Curiosity is standing to take this picture, a billion years ago might have been underneath that much rock. And this mountain, by the way, that's in the middle of the Gale Crater, you can't see the top of it. You're actually just seeing the foothills, is 18,000 feet tall. 18,000 feet tall. And so what you're looking at right here is at least some 10,000 feet high. Those hills down there, 400 or 500 feet for those tiny ones in the forefront. Those are ones that the Curiosity rover has actually gone over there and climbed up a little ways into this now. And it's looking at the different kinds of rocks that are found in different layers that represent different time periods in Mars's history. But, you know, at the bottom line is dynamic, but boy, sure change is slow, right? And what you see today is probably what's going to be seen by people from 100 years from now or 1,000 years or 100,000 years from now, basically going to see the same thing. I guess unless humans go there and terraform the planet and, like, you know, add water back to it or something like that. Not many changes are going to happen. And Mars landscapes are themselves much older than those on Earth, right? So this landscape, this image you're looking at right here is probably a very similar picture that you could have taken 10 million years ago, maybe 50 million, maybe even 100 million years ago. Curiosity rover could have landed here and taken a very similar picture. There's nowhere on Earth where you can say that same thing. There's a few places on Earth where there's extremely old rocks, right? But even they have eroded to a great extent. The actual rocks themselves are old, but the formations that they're in are not 100 million years old because there's a much faster pace of erosion on Earth. And the rest of the Earth's surface is much more dynamic, right? Because of water, because of other forms of, well, because of earthquakes, because of sedimentation, and then earthquakes and plate tectonics that are pushing up continents, creating more erosion. There's just recycling. I mean, most of the planet has been recycled in 100 million years, such that most of the mountains that you see and most of the other formations that you see are less themselves than 100 million years old, and many are much less than 1,000,000 years old. Most everything you see on Mars is in the millions of years old range in terms of, like, that actual hill is 1,000,000 years old the way it looks now. Hey, just a quick reminder here, I'm doing a whole series of videos on different aspects of Mars geology and how it relates to questions of, like, the appearance of age hypothesis and young Mars creationism, the whole question of the age of the solar system versus the age of the Earth. But really looking at the age of Mars is like a proxy for asking questions about the age of the Earth and how creationists view these things. And so I have a number of other videos already recorded. So can you spot the difference looking at a specific site and asking questions about how quickly that particular location might change? Very similar to what I just talked about now, but sort of at a different location. I talk about craters. How old are they? How can we tell how old they are? Are they days, years, centuries? And I'm actually talking about perceptions that people have of time and how difficult it is for us to, it's hard for us to perceive, like, how that crater could be 100,000 years old. And then I also have another video on, can ice layers tell us about the age of Mars? Looking at ice layers that are expressed in the sides of craters and talking about how long ice and a little bit about the water on Mars. I've got that and a bunch more videos coming up in which we take a look at some of the spectacular geological features of Mars and ask questions about their origins. With that, and I'll see you when I see you. Bye-bye.